Hey, everybody. Long time no see, right? So here we've got the first of our two videos that have a little bit to do with the physics of music, which is actually, for me, something near and dear. I played musical instruments all the way through elementary school, high school, even into college. I was actually a violin player and electric bass player. Shh, don't tell. But anyway, so this is just a basic introduction to kind of, I guess if you are a musician, you would call this music theory, and it's the physics of sound. If you're a physics person, you're like, hey, this is just how waves work. But this first one is kind of more about reflection and resonance and sort of how waves get generated in these particular contexts in of the context of musical instruments, and there's some funky things. And then the second part is a little bit more, again, kind of more about phenomenon having to do with interference, superposition, more about different types of instruments and why they have some different tones and things like that to it. So a little bit more of an application phase. The second one's a little bit shorter than the first one. So once again, just kind of keep that in mind. So the first thing I want you to kind of get out of this is that when we're talking about waves and how waves relate to musical instruments, first things first is that there are actually, for the purposes of what we're doing here, three types of instruments. Yes, I know there's percussion and there's all kinds of other stuff. What we're doing here, the wave generating instruments that use actually different types of waves to generate different pitches. Again, everyone's like, well, what about a percussion instrument? Yeah, I know those produce waves too. That's not what I'm referring to. Anyway, so with these, there are three categories of instruments are right here for the most part. So number one are going to be the stringed instruments. They have one particular way of producing resonant frequencies that are important in how they generate pitches. Pianos, by the way, are a stringed instrument. They're a combination of a string and a percussion instrument. If you've ever never looked inside one, those are actually all strings inside there. And when you press a piano key, an actual little hammer goes down and hits a different string that's inside there. So they're kind of a percussion and stringed instrument, or typical stringed instruments like those. Our second category of instruments is typically what people would call brass instruments, although that's not 100% correct. But the horns are typically this type. And these are what we would call open pipe instruments, where wind enters one end, there's a tube that basically makes the entire instrument. And then there may be different keys to effectively change the length of the tube. But then all of those would be considered to be open pipe instruments as opposed to stringed instruments. And then our third category of instruments here is actually technically closed pipe instruments, where they have some sort of a closure at one end and then an open at the other end. Typically, we would call these reeds, or woodwinds are typically what we would call these, but flutes are in the wrong category. So flutes for physics are actually similar to horns. They're in that brass kind of category because they're actually an open pipe on both ends. You've got wind in, wind out. All the rest of these, the reed functionally closes one end, and then you have to kind of make that reed vibrate, and then the other end of it is the open side of it. So we've got strings, open pipes, and closed pipes, and each one of these has a kind of a characteristic way that they produce resonant frequencies. In other words, you've got a wave in that reflects back, and then it amplifies itself. And this is an important characteristic of how these things actually generate tones that we can hear in the different types of tones. So in order to understand this concept, we do need to go back and kind of revisit this concept of standing waves. All of the type of instruments produce standing waves. In other words, a wave that goes out and comes back and produces a sequence of nodes and antinodes that's relatively stable in position, that actually doesn't literally vibrate through there. They're really kind of bizarre. If you haven't had a chance to yet, I would strongly suggest you get on YouTube and see if you can find some videos of standing waves. It'll make it a little bit easier to see. It's definitely an in motion kind of thing, and trying to look at a still picture of it doesn't work great for this. And I can't get GIFs to work inside this particular. Anyway, video's long enough as it is. So with this, these examples on the screen right here actually relate to stringed instruments, is how these things would work. So you can imagine that you've got a wave that's traveling one direction and it reflects back the other way. So our two key terms here, and these are important in the context of music, is the context of node and antinode. So an antinode is maximum displacement or maximum positive pressure, I guess, or positive to negative pressure. So it's the maximum changes, the highs and the lows. And the nodes would actually be kind of average zero spots in a sense. And these are the ones that they sort of cancel each other out. So nodes versus antinodes. Being able to recognize these is really important in being able to draw and recognize these features. So with a stringed instrument, one of the concepts of this is that you're going to have something like a node at either end. And so you can imagine if you have a half of a wavelength come out, it's going to hit that side. When it hits the opposite side, this functions like a fixed boundary. Therefore, the wave pulse reflects back inverted. So it comes back that way. And then it hits this side and it inverts and it goes back that way, hits this side, inverts, come back this way. And if you do it just right, with just exactly the right wavelength here, it will actually create amplification, resonance, and you'll have this beautiful standing wave that'll do here. This is one half of a wavelength. Here's a whole wavelength. It starts, has a crest and a trough, and then goes back to start again. And again, because you've got a node at this end, you've got a crest to trough, and then you're kind of back to neutral here. But when you reach this other boundary, because it's a fixed type boundary, it's going to reflect back inverted, and you get the mirror image of that wave. So this is what a resonant frequency would look like with one full perfect wavelength. And then you can get a wavelength and a half, and you can get two full wavelengths. So for me, when I'm looking at these, when I'm thinking about strings, any one of these little eye-shaped things is actually one half of a wavelength. I'm going to write this on here. One half of a wavelength is actually what's present. This right here is one full wavelength all the way across. So here's a half, here's a second half, here's a third half. Then you've got three halves of a wavelength is kind of, oops, if I do that wrong. Three halves of a wavelength is vibrating in here. And then here you have, there's one, there's two, there's three, there's four halves, otherwise known as two wavelengths, is actually setting up a standing wave there. So this is going to be kind of a key thing to kind of get used to seeing these sort of node patterns when we're talking about reflection and resonance. But this is the key part, that when these waves are just the exact right length, they will bounce back, create these standing waves, which will create these loud sounds, these resonant sounds that you then perceive as being a musical note. That's really what it comes down to. So with these, here's our three different kinds of instruments. So we've got strings, open pipes, and closed pipes. So this, I'm not going to spend a ton of time on this. It's going to be too much information for this particular video. The video will get way too long. So an important piece that's kind of behind my picture right here is that we are going to have our second Google Meet of this particular unit. The first one will kind of cover 15.1, just sort of general sound characteristics, etc. The second Google Meet is going to be really critical because it's going to help coach you through doing this this assignment, which is basically drawing and analyzing these waveforms. So like I said, I'm not going to spend a bunch of time with it here. I just want to point out that you need to come to the live Google Meet. The second one, it'll probably be Tuesday or Wednesday. And then, or you can, I'll try to record it and then you can just take notes from it. But it'll coach you through doing this assignment. And this assignment directly looks almost exactly like what's on the screen right now. So again, I'm not going to spend a ton of time doing every single possible interaction in here because it'll take way more time than you want to sit through right now. So come to the live Google Meet and I'll coach you through it. So anyway, with strings, here's the key things to look at in these patterns. A, there's always patterns. Number one, always, always, always patterns. Number two, those patterns always relate to wavelength. The second part of that is that the wavelengths are going to be related to how long the string is. They use the phrase L for this. So L is basically how long is the string or how long is the pipe. And that would be like from the left side to the right side of any of these diagrams would be considered L in terms of what it is. So like from here, if I can get it to start to draw from here to here, that would be L. In other words, the length of that particular string. Or from here to here, that would be considered L of that open pipe, or from here to here. So again, it's the relationship between the wavelength of the sound and the length of the resonator or the instrument that is trying to make that sound. That's the key part. So if you take a look at strings, here's the key point. If you look at strings, because of the ways that strings resonate, strings have a fixed boundary at both ends. You can't have an open-ended stringed instrument. They're always tied down to something. They're fastened to a key on one end and a bridge on the other end somehow. So there's always a fixed resonance pattern on these things, or a fixed boundary for reflection. So when you draw these, the key point is there's a node on the left, a node on the right. Always, every single time. That's the way that they reflect back in a way that sets up a standing wave. For open pipes, you can probably see here that it's kind of weird. It's exactly the opposite of strings. So with open pipes, open pipes act like soft boundaries on both sides because it's an open pipe, right? There's nothing that for this wave to literally bounce against. The wave is in a sense bouncing against the edge from being constricted within the pipe to being unconstricted outside the pipe. And so in order to get this to reflect back and invert, you actually have to have an antinode at the ends. And so you can kind of see that you've got this maximum here, and then you've got the same thing here. Those are antinodes. Take a look at it in this one. It's a little bit easier to see. And then there's a node in the middle someplace, and these have nodes in the middle. But all of these, if you take a look at it, you've got an antinode at the end. That's the only way that resonant waves, standing waves, will set up in an open pipe is if you have symmetrical antinodes present at either end of it. And then you can have any number of things on the inside. Again, one of these little eyeball shapes like this is considered to be a half of a wavelength, which means that one of these, this shape right here from here to here, is actually a fourth of a wavelength. So that's an easy kind of a landmark, a visual landmark to look for. So in these, you've always got these really easy half wavelengths. There's 1 half wavelength, there's 2 half wavelengths, there's 1, 2, 3 half wavelengths, here's 1, 2, 3, 4 half wavelengths. In here, they're a little bit harder to count. So every one of these pointy ones is a quarter of a wavelength, or you can think of it as every bow tie, if you want to think of it that way, is kind of is a half a wavelength. So there's a quarter and there's a quarter. So this whole thing is a half a wavelength. Here, there's a quarter, and then this middle thing is a half. So a half, a quarter, and a quarter is 1 full wavelength. Here you've got a quarter and a quarter. So each end is a quarter, a quarter is a half wavelength. There's a second half of a wavelength, and there's a third half of a wavelength. So you get 3 halves. Okay, closed pipes are the asymmetrical ones. And then closed pipes are weird because they're closed on one end and open on the other end. That's what closed means. So this would be like the reed end, and this would be the open bottom end of the instrument. Like if you got a saxophone, this would be the end that you blow in, and this is the horn looking end on it there. So on the reed end, because it's closed, you have a node on the closed end, and then you, just like the open pipes, you have an antinode on the open end. That's how these things set up in order to resonate. So again, they're weird, they're asymmetrical. So with these, now you've got one of these pointy shapes, and one of these pointy shapes is a quarter of a wavelength. So that's that first resonance that'll work on there is a quarter of a wavelength. And in here, you have these weird odd numbers. Here is a half of a wavelength. There's half a wavelength. And then here's one of these pointy ones. So this is a fourth of a wavelength. And this is actually 3/4 of a wavelength. This one down here, you've got a half. There's another half. And then there's a fourth. So this is 2 quarters. This is 2 quarters. So that's 4 quarters. And then there is the 5th quarter, 5/4. You can kind of see the n equals 1, n equals 3, n equals 5 kind of helps you see that pattern. So this is 1/4, 3/4, 5/4. There's a pattern every single time. 1 half, 2 halves, 3 halves. This is also 1 half, 2 halves, 3 halves, and 4 halves. This is 1/4, 3/4, and 5/4. So it's weird because it's only the odd numbers. So again, it's a little bit different how these things go. But again, that's the thing. And I'll coach you through drawing these on the other one. I just wanted to kind of show you an overview that these 3 different types of instruments have some different resonant wave patterns or some different standing wave patterns. Strings are characterized by a pair of nodes. Open pipes are characterized by a pair of antinodes. And then closed pipes are characterized by one of each. So again, one more time as we're doing this, this is an introduction so that you can kind of know why you need to come to this Google Meet that we're going to do on Tuesday or Wednesday. I'll post the date there for you. Is that there are these patterns that you're going to see that relate to the strings themselves. I need to move my picture out of the way. Move this down here someplace for now. So anyway, again, this would be a string because you've got a node and a node, right? Nodes at either end. And then a half of a wavelength is equal to the length of the string. Again, if they're talking about this is the string that we're representing, there would be a string in the middle, vibrating up, vibrating down. 1 half of a wavelength equals string. And you can kind of do some algebra with this. And that's all we're going to do in this thing is I kind of start playing around with that. So the algebra here is that 1 wavelength is equal to 2 times the length of the string. That's all it is. It's just algebra. And then they start combining this because in sound, a lot of times we talk more about frequencies. So then you're sort of rearranging these equations to rearrange for frequency. So if I take this equation and start to plug in my this piece into here, I end up with this particular looking thing where I get the frequency of this is the speed of sound, there it is right there, divided by the wavelength. And the wavelength is 2L. So there it is right there. So this thing right here is called the fundamental frequency. And this is an important pitch to know. Fundamental There you go, T-A-L. That's why I have it with a capital F. A fundamental frequency is like, imagine a guitar. When you just strum on the strings and you don't press on the frets anywhere, you're just doing an open string note. That's the fundamental frequency. Or if you have a trumpet or whatever, and you go through there, sorry, that's probably really loud. That's the fundamental frequency of that particular thing. You're not pressing any of the keys or doing anything fancy. So fundamental frequency. And then the key pattern on here, again, we'll go through this more in the other the webinar that we do, because each of the wavelengths that's in here is a pattern. The math sets up a pattern. When we start to solve for these frequencies that actually resonate, that sets up a pattern as well. Notice how I use lowercase f for these. These are called harmonics. The harmonics are simply multiples of the fundamental frequency. And again, it has to do with the patterns of recognition that goes on there. So if I know what the fundamental frequency is, let's say it's 100 hertz, then the first harmonic would be considered 200 hertz, and then the second harmonic would be 300 hertz, or the second harmonic, the first harmonic is the fundamental frequency. Second harmonic would be 2 times that, third harmonic would be 3 times that, fourth harmonic 4 times that. So there you go. Some patterns in fundamentals and harmonics, and I'm going to encourage you very strongly to try to come to the webinar where we go through that assignment with drawing these. Part of your assessment will be drawing some of these, and then there are some homework problems that have to do with this math kind of stuff that's on here. But remember, when you're doing an assessment or something like that, you can draw write these equations on a piece of notebook paper, and so you don't have to worry about it too much when you're taking a test. Okay, so there you go. I believe I'm done. Yep, that was it. I'm done. So there you go. Have a good one, and I will see you in part B of this, where we'll talk about kind of how this applies directly to musical instruments. I hope you enjoyed that, and I will see you guys soon. Right, there you go. How do I hit stop? Oh, there it is.